Hi everyone, so this is going to be the start of our video lectures into chapter 15. We'll see as we start to go through the material that it's dovetailing, it will dovetail very well with chapter 14, which was dealing with chemical kinetics. And then when we eventually get there to chapter 16, we'll see there's an obvious transition to talking about acid-base chemistry based on the theory that we'll present in chapter 15 on chemical equilibrium. So let's see, sometimes switching between programs, there we go. So let's start how we usually start most chapters, by defining what the title of the chapter usually means. So we're looking at chemical equilibrium. So this is going to be the state reached when the concentrations of reactants and the products remain constant over time. So that's going to be our macroscopic view. So macroscopic, if we remember, that means large scale. So over time, if we're just monitoring concentration, over time the concentrations of reactants and products will remain constant. And we've actually already seen an example of this back in, I believe it was chapter 11 or 13 now, I forget, but it's vapor pressure, right? We defined vapor pressure if we had a sealed container, and then let's say we had some kind of liquid in there. I'll just make that up, right? That liquid eventually can overcome its interactions with its neighbors and pop off into that headspace that's up here. And then we said the rate at which the molecules leave the liquid and enter the gas phase is going to be matched by the rate at which those gas particles slam back into the liquid phase until they both hit equilibrium. And we define that as macroscopic, I'm reading what I just wrote. We define that as a dynamic equilibrium. So what do we mean by that? So chemical equilibrium is just talking about concentrations. When we get to the microscopic view, so that's microscopic, we're also going to touch on a slightly different definition, but it's when the rate of one reaction is equal to the rate of another. So in this case, the rate of leaving versus the rate of returning. But we're going to focus instead less on PVAP, which is a physical process, but more on chemical processes in the remainder of this chapter. So one example I like to start with is probably something people are familiar with, which is pollution. Used to be a lot worse. Things have gotten better, but things still aren't great. So what does cause some nasty colors around cities? So you'll notice in the summertime, things tend to be more hazy and more brown. Boston's usually not that bad anymore, but I heard stories from the 70s from my dad where you could literally see a yellow haze sitting over Boston from Ward Hill in Haverhill, which is like 35 miles away. So let's hope things keep going in the right direction. But this is our example. So why only on hot days does the brown smog show up? Well, it's because there's pollutants in the atmosphere. In this case, we call them NOxes. You guys we did this in Chem 1101, the lab, when we generated that brown gas. We called it NOx. It's usually a mixture of nitrogen and oxygen. What I'm giving you here is just a very specific example of interconversion. So it means they're changing between two NOx compounds. In this case, N2O4 and NO2. So when things are colorless, what we'll see is we have this compound here with this structure. And that's my N, right? So each of those blue ones are N, and each one of these are an oxygen. So there's my N2O4. And that's on a nice colorless day. So I'll say low temp. Maybe it's autumn, maybe it's fall, spring, whatever, right? But typically on hot summer days, what you're going to start to see is that the air starts to become brown. Why? Because a chemical reaction happens when this N2O4 breaks down, literally by breaking a bond to form these new compounds. So 2 moles of NO2. Oops, should be an N. 2 moles of NO2. However, what you'll notice here, instead of having a unidirectional arrow to represent the reaction, I've written a double-headed arrow. This symbolizes equilibrium. that means we're going to have a forward reaction, depending on how you define it, and a reverse reaction. They're going to be competing between each other, and these reverse and forward reactions are going to be dependent on several different factors. We'll find out about pressure, temperature, amount. That's basically what the whole chapter is on. Why does this happen? But knowing that you have an equilibrium between a forward and reverse reaction helps us understand why we'll see low, colorless and low temperature, and then brown in the summer, because what's happening is that increased temperature is actually driving the reaction this direction. So it's saying under high temperature conditions, you're going to find a higher concentration of these NO2s than N2O4s. So what you see is an increase in browning of the sky. So if that's hopefully was an okay introduction. If it wasn't, this whole chapter, it's basically trying to summarize the whole chapter in one figure. We're going to be discussing each individual element as we go on. So let's first start off. We'll deal with dynamic equilibrium in a little bit, but let's start off by just looking at chemical equilibrium. All right, dynamic equilibrium is still technically a chemical equilibrium. It's just a refinement of what I'm talking about. Right here, this is like our broad macroscopic view. I can't spell today. But then again, that's every day. Macroscopic view. My bad. So when we're looking at the solution as a whole. So I still have that same reaction we were looking at on the last slide. So we know we have something that is brown and something that is essentially colorless, or I'll write down as clear. So if I start with some N2O4, that's what I see here, which is, somewhere, if I was going to guess, let me put that as, let's call it 0.04 molar. That's what I'm starting with. And I'm starting with 0 molar for the brown stuff, the NO2. If I let this reaction progress, what I see immediately is some of that N2O4 is being consumed and at the same time producing NO2. And that's what you'd expect. And the reason for this is because this reaction is being driven forward right now. Maybe I'll try to use different colors to help clarify what I'm drawing. Right? And that means when I started, because I started with something, and you can only have a reaction if something is there, it's going to start to progress towards where there's nothing. So it's going to start filling in this other side of the reaction, and that's what you're seeing here. Eventually, these two components will hit their equilibrium concentration. So I'll call that EQ concentration. You don't see that they're equal, it's just the concentration of the two compounds at equilibrium. We'll discuss later why the concentrations are not equal, because we're foreshadowing it's the rates that are equal, not the concentration. And then we'll explicitly detail why mathematically that's the case. However, let's start with however. That's just one case that we can look at, where I started with some of my reactants. If I start with just NO2, so I'm just starting with reactants, and it looks like I'm starting with, I don't know, let's estimate that as around 0.08 molar. That's here. And then 0 molar for the N2O4. This reaction actually happens. The difference is we've just written it in a way that we're not used to. Yes, by definition, it's correct to say the things on the right-hand side of the balanced chemical reaction, this thing here, the 2NO2, is technically our products. But if we have products and no reactants, and the reaction is possible, the reverse reaction happens. That's what we're looking at in the second figure. So let me clean that up a little bit. We're starting with a little bit of my NO2. I'm starting with none of my N2O4. And immediately what we see is that the products actually start getting consumed and start regenerating reactants. And eventually, they will hit their equilibrium concentration. There's my EQ concentration. Again, they're not the same. However, under the same conditions, they'll actually stop at the same place. Doesn't matter what I start with. And we're going to spend a little time talking about why and seeing more examples of that. So hopefully, it looks like that visualization was a little bit slow, but that's exactly what the dotted line is showing. we're talking about the reaction under the same conditions, not the same initial conditions, just the same reaction conditions. And we're finding out that even though if we started with only my reactants or only products, they're going to end up with their same equilibrium concentration. And we'll talk about reasons why that deal with temperature specifically. But that's going to be when we get a little bit further. It's going to be linking in, if you guys guessed it, the Arrhenius equation, but that's for later. Right now, all we need to know is that under the same conditions, they're going to have the same equilibrium conditions. So let's switch our focus now. Instead of looking at concentration, right, now I want to look at this idea of dynamic equilibrium. This is when we were looking at rates. So instead of having some sort of concentration where the N2O4 and the NO2, that is their equilibrium concentration given the conditions, it's much more intuitive, at least to me, to monitor the rate of reaction. So our forward reaction here is going to describe exactly what we saw on that last slide that we said, oh, that is our forward reaction. I wrote it down initially as N2O4 gas is converting into 2NO2. And on our first figure, that made sense because I started with some of this N2O4. For us, and I'm going to use the IUPAC way. So IUPAC is the International Union of Pure and Applied Chemistry. It kind of dictates how we use symbols. So the forward reaction is usually represented by little k sub 1. So there's our rate constant we've seen again. It's the exact same rate constant we did all our work with in chapter 14. We saw in that second figure, though, if I started with an amount of NO2 and a reaction is possible, the reaction could be forced to run in reverse, and we will call that K minus 1. Other books might write down K1 as K forward, and K minus 1 is K rev for K reverse. That's other common notation. But what this is looking at, we know I can plug K into the rate constant equation, right? Our generic rate law is K times some reactant to some product, to some exponent. We've done that a bunch. So if I know my K's and my concentrations, and if I'm assuming I know my rate law, I can immediately back calculate out rate. So that's kind of I'm trying my best with limited slide switching to help bring topics together. But ultimately what this slide is to show is that if we can plot the rate, this is the rate of the forward reaction. When it has hit dynamic equilibrium, the rate of the reverse reaction, even though they're different, this whole time here they're different, at a point, and this is where in the figure it switches over to purple, their rate of the forward and reverse reaction are equal. So, at equilibrium, rate forward equals rate reverse. And so actually what you'll see is only for the K's are the numbers used for forward and reverse. A lot of times rate is more commonly given the FOR for forward and rev for reverse. You did not hear me say K1 equals K minus 1. That is not what I'm saying. I'm saying the rate law. So if I did do something like K forward, K1 times A raised to some exponent. I'm talking about the rate, not the rate constant. So forward and reverse do not have to be equal. Occasionally they might, and that's a rarity, but it's that's not what I'm saying. I am saying rate forward equals rate reverse. So let's tie everything that I just talked about together into one concept. This is going to be the equilibrium constant. So in both slides, the first example that I was talking about, right, we were dealing with concentration. And that's what I was saying, that's our chemical equilibrium. In part 2, I was talking about rate. Can we unite these ideas into one, meta idea? Yes, we can. That's going to be, I kind of did it out of order. That is what the equilibrium constant is. So, let's start. You know what I'm actually going to do? I'm going to skip forward a couple of slides and do this out slowly. but you can come back to this. Effectively, what I'm going to write is exactly what you see here, but sometimes writing slowly while I'm doing it helps students. So what I want to do is I'm going to take some kind of generic reaction. I'm going to call it, we'll say, I'll write it at the very top. It's going to be AA plus BB has a forward reaction and a reverse reaction. So it's an equilibrium with CC plus DD. I'll call the forward rate constant, keeps hitting the top of my screen. I guess I cannot do it there. So let me wipe that. I'll just do it really quick again. So we have AA plus BB equilibrium with CC plus DD. We'll have some forward rate constant. Wow, I keep getting out of that. Hold on, my writing software just stopped for a second. There we go. We have my forward rate constant and then my reverse rate constant. And again, I'll put that up here. K1 is forward, K minus 1 is reverse. And that is the standard way that most rate constants are written when there's multiple rate constants. So if I'm only looking at the forward reaction, that means if I wrote this rate law, rate forward equals K1 times A, we'll discuss this a little bit later, to the B, right? I could write out that rate law. This is a little bit strange, but when and only if your reaction is at equilibrium, like we see here, do my coefficients in the rate law match the balanced chemical reaction. We didn't get into it because we didn't focus on reaction mechanisms, but once things have achieved equilibrium, that's another way of finding out what the exponents are in the rate law. So only if you see the double arrow can you write out the rate law as the coefficients as the exponents. So let me back up from all that. So that's our forward reaction. Now we can have also a reverse reaction. And I can do the exact same exercise, except now I'm looking in the reverse reaction. So my rate reverse is going to change my perspective. My rate constant is now K minus 1. And technically, because I'm flipping my perspective, I'm going to write C and D where I would usually put the reactants. So now I have a forward and reverse reaction. So let's first bring in this idea that at equilibrium, rate forward must equal rate reverse. That is the definition of dynamic equilibrium. Well, I have a rate forward and a rate reversed. Let's set them equal to each other. So I'll keep black for the forward. So there's my K1, A to the 8th, B to the bth. That is equal to the reverse reaction, so there's my K minus 1, C to the cth, and D to the dth. What I want to do now is I'm going to get all of my K's to the left-hand side and all of my concentrations to the right-hand side. So let me do that. That means I'm going to bring all the K's to one side, so this is my K1. Oop, I said I would keep them with correct color. With my K minus 1. So you can see all I did was bring down this the K1 over the other side. That leaves me with my numerator still C to the cth, D to the dth. But now I'm going to pull over my concentrations from the forward reaction. A to the 8th and B to the bth. This is going to be our equilibrium expression. Occasionally, and sometimes you might see this in my notes pop up sometimes, is called the mass action equation. The name comes from, let me spell this first, instead of trying to spell and talk, right? The name comes from that it literally, it's saying massive particles have to move for equilibrium to be achieved. Massive just means something has mass. All compounds have mass. Action means they move. So that's where the name comes from. So I'm going to wipe this screen real quick. So hopefully take some time to catch up and write neatly in your notes. But what I'm going to do is I'm going to take this bottom equation and then kind of pull it apart just ever so slightly. Maybe not even pull it apart. Let's just start by first rewriting it a little bit more clearly. Oops. So we have our expression, d to the dth all over a to the 8th, b to the bth. So if we look at our left-hand side of the equation, I got two constants there. Constants don't change, and we know at least the little k, the rate constant, doesn't change unless you change temperature. So I'm going to group them together, and I'm just going to call this big K. And so this is why I was alluding to before, rate constants have a lowercase k. And I told you before, I'm going to start penalizing ever so slightly, the same amount for sig fig, if you can't keep your capitalization straight. Equilibrium constant is a capital K. So they have distinct meanings, right? So we want to make sure we can make being clear when we express that. So that means what I could also do is write that equation like this. And so now I can see I'm relating my concentration as a definition of equilibrium to my rates as another expression of equilibrium, and both will be equal to the same rate constant. We're going to start off by talking about something called, this is generically KEQ, but since we're dealing with concentrations, we can also substitute it with a C. Sometimes it helps the reader to know you're dealing with concentration, though that's not always the case. Just I want to make sure you know what the book is talking about. So now we have an expression for equilibrium. So that was our derivation work. Oh, kind of went backwards a little bit, but this is exactly what we're seeing, right? So my summary here. The big one is for us, right? Kc we said was going to be equal to K the forward versus the reverse. Another expression, I like to keep this really generic because people kind of get this confused. I pull it products over reactants. Instead of remembering all of this, because that can get a little bit messy and confusing, just know K equals products over reactants. Sometimes I'm even as quick as just writing it like this, as long as I remember to throw in my exponents. So if I was going to write out a KEQ, if I'm writing out the expression for this reaction we've been basically tracking this entire time, I know it's products over reactants, so my products are NO2. Well, that's exactly what I have here. It's a balanced chemical reaction. It's at equilibrium, so my exponent is going to be 2. And then I take a look at my reactants. My reactants go on the bottom, right? My reactants N2O4. For this one, it's balanced. The coefficient is 1. You can omit the 1 when you put it in the mass action equation or the equilibrium expression. So you can pull this directly from the balanced chemical reaction. This is going to need to be pulled from experimental data, which we'll talk a little bit more about. Waiting for my screen. There we go. Sorry. I have a small delay between my iPad and what's on the screen. So what this table is summarizing is this equation that I've now probably beat to death, but I want to make sure you guys are following. And I'm going to use P and R as products over reactants raised to whatever exponent they're at. So I'm keeping it generic, just so not to overwhelm what's being written on the screen. So that means if I don't change my conditions, and my conditions I'll care about are temperature, what we notice here, I'm going to give you a list of different initial concentrations. There'll be a list of equilibrium concentrations. I can separate those by a red line. That might help. And then I'll talk about the experimentally determined equilibrium constant. This will be coming from knowing the products and reactants, specifically at equilibrium. So I'm going to start off let me just erase some of this so it's not too distracting. I'll start off with some amount of N2O4 and some amount of NO2. In this case, an extreme example. I have all reactants, no products. Well, I can just wait until equilibrium is achieved and measure the concentrations. I can do literally the concentration of that raised to the exponent of 2. Take that, raise it to the exponent of 1, divide them, so you exactly see my equilibrium expression constant is right here. And I can solve for Kc immediately. Let me do that maybe a little bit slower because I was just talking through that, but if I did put in my equilibrium concentrations, I'll grab these two right here. I know my expression is NO2 squared all over N2O4 to the first. I plug in my numbers, my concentration at equilibrium. NO2 is 0.0125, and that will be squared, divided by N2O4 at equilibrium is 0.0337. I do that out, so I got 0.0125 squared divided by 0.0337, 4.64 times 10 to the negative third. It's exactly what you see up there. Take-home message from this slide, though. Look at all of these different initial starting concentrations. They're not necessarily equal to their equilibrium concentrations. And also, you'll notice all the equilibrium concentrations for each individual experiment might be different because I'm starting with different amounts. However, the equilibrium constant for all 5 of those different types of reaction, or different reaction conditions, are all the same. That is why it is an equilibrium constant. So it's not necessarily the equilibrium concentrations will always be the same, because it's all going to depend on how much you start with. Just you can predict what those concentrations will be because the equilibrium constant expression never changes. Oh, I already did that out. Sorry, I did it out by hand, but now we have it on the, as I already typed out. So you can see it in another way of comparing experiment 1 and 5. For this, the only take home from this slide has confused the heck out of my students in the past, and it really shouldn't. All this means is the expression for Kc that you will write is based on the chemical equation as you wrote it. So let's take a look. If I write here, I'm looking at this reaction. The way I have it written, these are my reactants. These are my products. I know it's always products over reactants. Well, there's my products. It's squared. My reactants are N2, the 1, H2 cubed. It's exactly what you'd expect. There's nothing new to that. That's what we just did on the last couple of slides. Sometimes you need to write out a chemical reaction slightly differently. Maybe it's easier to report to the reader, or maybe it more accurately represents what you're studying. So let's take a look at this second way I can write out the reaction. I'm literally writing the reverse reaction. That's all I did here. So I can see now, by definition, by convention, ammonia, the NH3, is my reactant, and then I have hydrogen and nitrogen as my product. I need to follow my rules. Products over reactants. Nothing changed. What is different, though, is talking about the relationships. Because I wrote it in reverse, Kc for this reaction is now the reciprocal of the original one. Don't get lost in that minutia. I'm not worried about that. I'm more worried, can you write out the Kc expression given exactly how you've written and are communicating the reaction to your reader? Again, sometimes you might have to change the coefficients. A lot of the times reactions are reported as the minimum, the lowest common denominator. Sometimes it's easier to show stuff, maybe if you don't have fractions or something like that in your balanced chemical reaction. You want to get rid of them and have all whole numbers. Or maybe for whatever reason, like I've done here, multiplying by 2 makes it easier for the reader to understand what you're trying to get across. Here it's just for an example. But again, I take a look. I have my products is ammonia. My reactants are still N2 and H6, but I follow my rules. Products over reactants. I wrote it this way as instead of, having 1, 3, and 2, I did 2, 6, and 4, right? And so as you see here, I'm multiplying it by 2. Products, it's now written to the 4th. My reactants squared into the 6th. Again, take-home message. You are writing the K expression for exactly what you have written as your balanced chemical equation. And hopefully that goes unnecessary to say that it has to be based on a balanced chemical reaction. All right. We're getting very close to the end, guys, so we're almost done. Some nomenclature stuff. Kc, by definition, is concentrations products over concentration reactants. Kp is going to represent the same exact idea, except we're going to report it as the partial pressure of the products over the partial pressure of the reactants. It sounds more confusing than it has to be. We know I keep hitting the wrong thing. Sorry, hold on a second. There we go. We know PV equals nRT. We know concentration is N over V. So if I rearrange that, it ends up being P over RT, right? So we can actually go from partial pressure, which is P, as long as I know R, and we said T can't change or else I'm changing everything because all my K's change, right? So effectively, temperature needs to remain constant. So that means I got two constants here, R and T. I now have a relationship between pressure, which is the P, and concentration, which is moles per volume, which is equivalently to the idea of molarity. So that's why, don't let this confuse you. We said Kc is for units of concentration, specifically molarity. Kp is the same idea, but it's using partial pressures. Oh, excuse me. That is not getting sick, guys. I'm just talking. I've been recording a lot of videos today, so just dry throat. All right. So as long as we're clear on that, I guess I can drive it home again, but right, products, reactants, squared to the first. The only difference is, did I mention this? I forget now if I did. Concentrations use brackets, partial pressure. The only difference is you can use parentheses to represent it. So keep track of that. How do I convert between the two? On that last slide, I showed you that there's a relationship between concentration and pressure. I kind of just pulling together variables, right? There's two constants, and there's pressure and temperature. Did I write that right? Oh, sure. Wait. Don't want to give you anything wrong. Right, so you guys are actually seeing me actively think. So this is what I do when I'm trying to go through problems. So yeah, I can already see I flipped that upside down. So I'll just do this. Fix it. Right? All right. So, and wait, did I do that right? Oh, I was right the first. Oh, damn it. Sorry, guys. Been a long day. My bad. So just know from the last slide, there's a relationship between pressure and concentration. Luckily for us, it requires a little bit of calculus, so the book does it for us, and we're not going to do the calculus, but we can pull out this expression that relates Kp to Kc. The only thing new here, R is our gas constant. We just need to keep in track. Because we're deriving it from PV equals nRT, we want to use the value that we usually use for that equation. So we do know two R's now, 8.314 joules per mole Kelvin. And then we also have our original value for R, right? They represent the same thing. They have different units. That's it. Just keep your units in check. Other thing, too, we've been noticing a lot is with temperature, especially when we're deriving things from PV equals nRT, have to be in Kelvin. And then this new concept of delta N, only new because we've never seen it. Delta N is the change in the number of moles, specifically of gas. So change in number of moles gas. So it equals, going to be delta N for a reaction equals the number of moles of gas of products So that's my final, effectively, minus the number of moles of gas in my reactants, which you can think of as initial. Same idea as delta, final minus initial. So final, initial, if you want to think of it that way. But it doesn't get much harder than that other than plug and chug. So the last thing we're going to talk about in this particular lecture is going to be heterogeneous equilibria. So what does heterogeneous mean? Well, if we go back to 1101, we just mean it's a mixture of two different states, and that's exactly what we'll see. We have solid, solid, and gas. So it means somewhere in my balanced chemical reaction, there are differences in the state of matter. So if I wrote out the Kc for this expression, right, I have my products, calcium oxide and CO2, calcium oxide, CO2, in my reactants, calcium carbonate. I see that, we're in good shape. However, what you've seen here is that for two of the compounds, I replaced it with the number 1. Why? Well, if we take a look, anything that has the number 1 had the state of matter of solid. So solids and pure liquids do not appear in equilibrium expression. In any case, Kp or Kc, it does not matter. Why is that the case? We can get into it. There's more theory behind it, but a simpler way that I look at it is, right, you're talking about concentration in terms of N over V, which you can think of as molarity, right? If you're looking at a solid's its molarity, quote unquote, of a solid or a pure liquid is equal to its density. Chemical reactions do not change its density. So a density is an intrinsic intensive property. So intensive property, which it means it doesn't matter how much stuff you have. The density doesn't change. So if the density is not changing, technically the concentration isn't changing. If you can't change the concentration, there's no such, it basically doesn't include in the mass action equation where things are changing. So long story short, solid or liquid, omit from expression. It's as easy as that. All right, so this is the very last slide because this is a transition slide. This will get us into ice tables, which is pretty much the rest of the chapter. That's why I'm trying to isolate equilibrium constant by itself. The majority of the chapter will be based on using these numbers, right? So some things that we notice. So I have a reaction here showing water breaking down into hydrogen gas and oxygen. And I'm also showing a reaction. Well, let's look down at the bottom first. We'll look at the middle one in a bit. But now I'm going to look at the red reaction. This is actually the reverse reaction of the other highlighted reaction. This is hydrogen gas and oxygen coming together to produce water. So let's take a look first at the, let me change the different color here, at the equilibrium constants. So what we notice right off the bat is we're going from huge changes in numbers, right? 48 to 47, that is going through 94 orders of magnitude. That is a huge order of magnitude. So right off the bat, we realize we're dealing with things that can have a scale from very, very small to very, very large. But what is that telling me? So let's start with the very, very small first. So that's going to be the blue one up here. So if I write out that equation, the equilibrium expression, so K, of that blue one at the top, I would realize that it's H2 squared O2 to the first divided by H2O squared. And so there's my equilibrium constant. I can keep my the water as part of the expression because we see it's actually homogeneous equilibrium. It's all talking about gas phase, so nothing's going to drop out. If I look here, when I have a K that is really, really, really smaller than the number 1, which is what I have here, 10 to the negative 48th, you don't even care about this number per se right now. You just care about the order of magnitude. It is incredibly small. Well, to get a number incredibly small, that means the denominator must be much, much bigger than the numerator. Denominator in this case is reactance. A tiny equilibrium constant is telling us the equilibrium is heavily favored to the right-hand side. So heavily favored toward reactance. And that makes sense. Why? Well, because it's a reaction we're probably all kind of familiar with. Water, if you just let it sit there, doesn't spontaneously turn into a flammable gas. We know that doesn't happen. However, if I look at the reverse of the reaction, which let me do it in red so it matches up what's on the screen. But I do the K for the reaction that's down here, which is the reverse reaction. It's still products over reactants, so there's my product of water squared over my reactants, which are hydrogen and oxygen. Except now my K is really bigger than 1. That means my numerator is much bigger than my denominator. My numerator in this case happens to be products, which is water. This should also make sense because we take a look at the reaction. This is the combustion of hydrogen gas. We expect that to be favorable. We've seen that reaction, probably not in real life. Well, we might have. But it's definitely, that's like the definition of combustion. It means it's definitely going to favor products, and that's what you'd expect. Oops, I should go back one more. That's a friendly reminder for myself, but one last thing to mention too is that not all K's are extreme. Some are closer to the number 1. So when you have a K approximately close to the number 1, that means the numerator and denominator are roughly equal. And so that means that, not necessarily, but it usually means the equilibrium concentrations of the reactants and products are roughly 1 to 1. Well, depending on how the numerator works out. But it's basically saying products and reactants are pretty close in amount. That's all it's saying. All right, so it was, again, a little bit longer. I'm still working on trying to make this as condensed as I can. This is almost like a 2-day type video, because if you look at the syllabus, we deal with equilibrium constant on 2 days. So I'm going to try to figure out what we're going to do with that, but the next thing we'll be focusing on is almost exclusively problem solving using these numbers. Right now, it's just understanding what is the equilibrium constant, how does it relate to equilibrium concentrations, and how does it relate to the rates of the forward and reverse reaction. All right, stay safe.